Hello and welcome to the second week of the Markov Chain topic. In the first week, we've talked about how we can define transition probability, which means the probability of transitioning or changing from a state in the system to the other state in the system. Now here we are going to see what happens if we are interested at not only one step, but several steps. So let's start with n-step transition probabilities. So this is the question that we'd like to answer. If now we are in a state I, what is the probability that n periods later, the Markov chain will be in state J? So the answer to this is called n-step probability. It is called n-step because what we've seen so far is the transition probability, which explains the transition in one step, from this time step to the next time step. So transition probability is one step transition. Now what we'd like to answer is that if we now, let's say in the gambler's win problem, let's say if we have $2, what is the probability that n games later or n periods later we will end up in state 0, for example? So that's what we're going to try to answer in the n-step probability. So let's use the notation to define the n-step transition probability. So here, given that now at time 0 we are at state I, what is the probability that at time n or n time steps later we will be at state J, which can also be denoted as Pij n in the parentheses. So n in the parentheses show the time steps. And then the first part of this equation simply says that the time doesn't have to start at 0. It can be at any arbitrary time step m. It's just that we are interested at the state at n times later. So here it just says that you don't have to start at 0. You can start at m. It's just that we're interested at n times later. Okay, so Pijn can be defined formally as the n-step probability of transitioning from state I to state J after n steps or n periods. And then what we've seen before, the transition probability, you can define it as Pij1 or just Pij, because it means the transition probability from state I to state J in just one step. Let's start by looking at a two-step transition probability. Means that we are going to look at the transition in two steps of time or two periods. So let's say we're interested at Pij and then 2 in the parentheses. This means that we're interested to know what is the probability that now at time 0 we are in state I, and then at time 2 we are at state J. We don't really care what happens at time 1. We only care that at time 0 we are at state I, and then at time 2 we are at state J. So at the time 1, any state is possible. It may include state I itself or state J. It doesn't matter. Everything that matters is just I at time 0 and J at time 2. So to calculate this probability, we can say that Pij2 equals the probability of transition from I to K, and K is all the possible states. So transitioning from I to any states that we have in the Markov chain times the probability of transitioning from K to J, right? And then remember, K is any state that we have in the Markov chain. So Pij2 equals transitioning from I to K and then K to J for all the possible Ks that we have in our Markov chain. So in other words, Pij2 equals to Pik times Pkj, in which k is all the possible states that we have in our Markov chain. Now let's see how we can obtain this Pij2 from the transition probability matrix easily. Let's say I have a Markov chain that involves S number of states. So the states are 1, 2, 3, 4 up to S. And then I would like to know what is the probability of the transition from state 1 to state S in 2 steps. So here, this is how you can do it. So this is matrix P, and this is also the same matrix P. So following this formula, if we want to compute the transition from 1 to S in 2 steps, first we need to see the probability of 1 to all possible states. So that is shown by this row. So that is row 1 to any state that we have in the system. For 1 to 1, 1 to 2, 1 to 3, 1 to 4, and all the way up to 1 to S. And then this formula says that we need to multiply the probability from all states to J. So our J here is the state S that we're interested at. So we're looking at this column, right? Because this is 1 to S, 2 to S, and then S to S itself. If you multiply this row and this column, you actually are doing the computation of this formula. Because from I to any state that you have in the system times any state in the system to the state S. So that multiplication will define PIS in 2 steps. If you do the multiplication like a matrix multiplication, the row times the column, row times column, and then you may identify PIS2 as that element. So this P squared matrix can be used to see what is the Pijn. So you just check the ijth element of P to the power of 2, because we are looking at 2-step transition probability matrix. Okay, so let me recap. We're interested at PIS in 2-step. So what you do is you multiply P and P again, and then you look at the element of 1 of the row 1 and the column S. Now, if you are looking at the transition probability in n steps, what you do is just you keep multiplying P such that you get the matrix of P to the power of n, and then you just check the ijth element, so the row I, the column J that you are interested at. So again, to create an n-step transition probability, you just need to create the matrix P to the power of n. And what you need to do to create it is just you keep multiplying the matrix P. So P times P times P times P again until n times, which equals to the n here that you're interested at. Okay, so let me ask you a question to check your understanding about 2-step probability. So given the P squared matrix, here you're given the P squared matrix, I ask you what is the meaning of PIS2. As usual, I will give you a pause in the video to give you time to think about the answer, and I will give you the answer after that pause. So the answer is A. PIS2 means that the probability that now at time 0 we are at state 1, and then at time 1 we can be at any state from 1, 2, 3, 4 up to S. And then at time 2 or 2 steps from now we are at state as